this. Welcome back to Organic Chemistry. We need to get excited for this final push for the next week. Obviously, we have Thanksgiving coming up. And so hopefully we will all stay isolated and well through the Thanksgiving holidays and come back strong and ready to go into our final week and our finals exams. Okay. So this week, I'm going to do 2 lectures on radicals, and then I'm going to start module 11 on Friday. So that'll give us Friday, Monday, and next Wednesday, which is a class day, unfortunately. And then we'll have all of those as our number 11. We'll then do an activity on the 30th, which is also a review. It's basically reaction tables. We're going to start tabulating all the different cool reactions we have and look at their specificities. And so I believe they've already started doing that in some of the SI sessions. So I'd highly recommend going to SI sessions through the end of the semester and start looking at that kind of stuff, because it really helps kind of organize things in your head. Okay. So for this week, all we have is our chapter 10 that we'll be doing here. We'll start chapter 11. So go ahead and start reading chapter 11 Wednesday-ish. Our module 10 homework is not due until Monday the 16th. And then note that is the reading assignment, and it's all on Top Hat. Okay, are there any questions about administration or what we're going to be doing this week in class? Okay, well, my chat room is open and working, and I've got I'm about to pull up my slides right here, and we'll start those now. All right, let me share my screen. And pick out one of my favorite styluses. Styli. It's the green one. Anyway, so now we're going to talk about radical reactions. And up to now, all of our mechanisms included a double barbed arrow, meaning 2 electrons were coming in or 2 electrons were leaving. All of our nucleophiles had a pair of electrons trying to form a new sigma bond. All of our leaving groups left with 2 electrons so that it formed a negative charge. So everything we've been dealing with here is involving 2 electrons moving in or out of the system, with the one exception of the anti-Markovnikov's addition of HBr across an alkene. Now, when we did that, that was a radical reaction. And I told you we'd talk a little bit more about that in module 10. So here we are, radical reactions. And the key to radical reactions is the fact that instead of moving both electrons around and creating new sigma bonds, we're actually going to move single electrons around, creating new bonds and creating new radicals. Okay, so we need to learn a little bit more about their stability, their reaction, and there's actually multiple steps in a radical reaction, because of every time you react a radical with a neutral species, you end up generating a new radical. So we have to follow the radicals as they go, and we have to figure out how the reaction ends. Okay, so let's define radicals. Radicals, or free radicals, are any atom, group of atoms, molecule with 1 or more unpaired electrons. Okay, so you can actually have 2 radicals on the same compound. The key is that they are unpaired. Okay, this unpaired electron right here, look at our Lewis dot structure here. This unpaired electron is significantly more reactive than our regular nucleophile or electrophile, because those can be stabilized by solvents and stuff like this. In this case here, they react differently than electrophiles or nucleophiles, and therefore they're their own class of chemical reactions. Okay, so if we look at the structure of these free radicals, if we look at a carbocation, we have an sp2 hybridized orbitals that are sticking out, giving us this trigonal planar structure here, and they're 120 degrees apart. And the orbital here is empty. Okay, so there's no electron-electron repulsion controlling the shape of those 3 things that are bonded to that central carbon. In the case of a free radical, we actually have 1 electron in that p orbital. And therefore, whichever side that p orbital is, that electron is on, has electron-electron repulsion and slightly changes the shape. So there's 1 electron, so there is a little bit of trying to go away from that electron, little electron-electron repulsion. And we get a little bit of bend, but not to the full, 109 degrees we would expect from an sp3 hybridized carbon. Remember, this radical is an sp2 hybridized carbon with one electron in that p orbital. Okay. Now, in contrast, if we go to an anion, we put a second electron in there. Okay, now we have actually even more electron density in that orbital than we would have in our sp3 hybridized. So it actually bends those sp2 hybridized orbitals down because we have both electrons in there. And we have more electron-electron repulsion, which means our radical is kind of halfway in between our planar carbocation and our pyramidal carbanion. Okay, so that means there's a little bit of specificity, but the key here is that single electron in that p orbital is going to do all the work. Okay, so how do we get there? Well, way back in chapter 1, we talked about there's two kinds of bond breaking. There is heterolysis, where one leaves with no electron and one leaves with the two electrons, giving us a positive and negative charge. Okay. In the other option we saw was what we called homolysis. Homolysis is where they both leave with the same. So they're both leaving the thing with one electron, giving us two radicals when we generate it initially. Okay. Now, so this bond dissociation energy associated with breaking these radicals is kind of important because it gives us a little idea on the enthalpy of the reaction. Okay, we're talking thermodynamics again, but the idea here is that the bond dissociation energy is positive for bond forming, meaning it's using heat to create that bond. It is negative for bond breaking. Okay. So when you break a bond, it is the enthalpy of the reaction is negative. Okay, so let's take that into account and look at our calculating our total enthalpy of a reaction. So let's say we have a radical reaction where we go from one equivalent of hydrogen molecule, diatomic hydrogen, and one equivalent of chlorine molecule, diatomic chlorine. And we're going to, by a radical reaction, break them apart and switch partners such that we have two equivalents of HCl. Okay, so whenever we look at this calculating the enthalpy of the reaction, we have to take the total change in enthalpy is equal to the sum of all the bonding energies of the reactants minus the sum of all the bonding energies, bond dissociation energies of the products. Okay, think about that. The reactants are what we end up with. So we have to, that final product has to be what we are subtracting our starting materials from. And so if we have a positive number, then we're going to get a release in energy. And if we have a negative number, it's going to be an absorption of energy. Okay. So let's do that calculation here. So if we have the bond dissociation energy of the hydrogen molecule to break it into two hydrogen radicals is 436. So that's going to be on this side right here. So, sorry, the reactant side here. Sorry, not the product side. Well, I think I said that backwards. So the products here. And so we have the reactant. So we have 436. So that's just breaking one equivalent of this to give us this. And then it's 243 kilojoules per mole to break this bond here. So at the end of this part of the reaction, we now have two equivalents of hydrogen radical and two equivalents of chlorine radical. Okay. Now, the next reaction is those two combining. So the bond dissociation energy of that is 432, but we have two equivalents of it. So we have to double that, which gives us 432 times two equivalents, gives us a net change of negative 640. Okay. It's negative 640 because this is the bond dissociation energy. So that's breaking it apart, okay? But we're putting it together. So that means it's the opposite of that. So we have to use the negative value, and that gives us a negative 864 kilojoules per mole. So that means the net result here is that we have a positive 673 kilojoules per mole and a negative 864, meaning that we release 186 kilojoules per mole. Okay, so now what's very important about this is we don't care what mechanism it follows. All we care about is the final state. So in this case, even if we weren't using a radical reaction, this bond breakage, bond reordering right here, it would still give us the same energy at the end. Okay, so being said, we have to look at only the initial step and the final step, because there are so many of these steps that happen during this reaction that we might not see all of the different species, and it doesn't matter. We can make and break bonds we can make and break bonds multiple times in the net of the reaction, but the net result is the transformation from our starting material to our product here. So in this case here, we're going to look at a slightly different reaction, and we're going to react methane with chlorine under this same radical condition, and we're going to generate methyl chloride and HCl. So we're going to take the chlorine, break it apart, and then form our two final products. So what that would look like is our chlorine is going to go to a radical. Then our chlorine, this can actually break apart to give two radicals as well. This radical can combine with this radical. So, okay, look at this. Each side has one electron. When you have two electrons shared between two atoms, that creates a sigma bond. So we're taking those two radicals and generating a new sigma bond. And we're doing the same thing on this radical here to get rid of all the radicals and end up with two neutral products. Okay. So when we look at that, okay, the breaking apart of chlorine, the diatomic chlorine, to its two radicals takes energy. It takes a lot of energy to get to that initial reactive state. Okay. Now, by taking those two radicals and making our final product with our new sigma bond, it actually releases a lot of energy. It releases 365 kilojoules per mole. So when we look at whether or not the product is a higher potential energy or a lower potential energy, that's what we need to do. So just like when we had an endothermic or an endergonic reaction, if the difference in them has the products being higher than the reactants, then the delta H is positive and the products are less stable and have a higher potential energy. Now, when the products are lower in energy than the starting materials, then we have a delta H is negative and we've given off heat in the system. Okay. And that the products are more stable than the reactants and we've given off heat. Okay, so if we looked at each and every step in that reaction, we're looking at actually the bond dissociation energies for each of those. So we had the bond dissociation energy for this. And remember, this is a reactant, so it's going to be the one that's breaking bonds right here. So this is going to break a bond to generate these. And then these two are going to form bonds. So they're going to be on this side of the reaction. So breaking chlorine apart gave us this 439 kilojoules per mole. Breaking the, right here. Breaking the hydrogen off the methyl group gave us this many kilojoules per mole right here. Oh, so sorry, chlorine and the methane, sorry, mixed them. And then when we recombine the chlorine with the methane, that's 350 kilojoules per mole. And when we recombine hydrogen with chlorine, that's 430 kilojoules per mole. The net result is a negative 99 kilojoules per mole. That means that the starting materials had 99 kilojoules more energy than the products. And if the products have less potential energy, they have to get off that extra energy as heat. Therefore, the reaction is exothermic, okay? And most reactions where you produce stronger bonds than the reactants are favored to go. Even if they create a higher potential energy, the stronger the bond in the product, the more likely the reaction is to progress to that stronger bond. And most of the time, that actually makes them exothermic. Okay, questions on that? So notice this is a little bit different than those heats of addition or whatever, because we're actually breaking individual molecules apart and then recombining it. And we're not doing it with pairs of electrons, we're doing it single electrons. Okay, so now let's talk about, now that we've broken them apart, we have these radicals. Let's look at the stability of these radicals. Just like we had stability in carbocations, where the more substituted carbocation is more stable, we actually have a similar kind of stability trend in the radicals. Okay, so in this case here, we're looking at the formation of a primary radical versus the formation of a secondary radical. And we see that the formation of that secondary radical actually takes less energy. Not a lot less energy, but less energy, meaning that secondary carbocation, that secondary radical is more stable. Okay, so the energy formed from that primary radical is greater than the secondary radical. So that means the primary radical has that higher potential energy, it's less stable, and it tends to be more reactive. However, if you have a reaction mixture, which product is more likely to form at a specific temperature? Because it takes less energy to generate this one right here, you're going to have a higher number of those radicals being formed, because less molecules had to have less heat to get to that first radical step. So the stability of these is a thermodynamic property right here. And it doesn't tell us anything about the rate of formation. It just tells you that that energy is less. And therefore, if you have more things getting that energy to be able to dissociate that bond, that's going to happen first before the reaction to form that primary radical is. Okay, so this is sounding similar to that carbocation formation, where the carbocation is more stable the more substituted it is. Okay, so we can actually go crazy calculating these bond dissociation energies and figuring out which way the reactions are going to go. And we have all these really cool tables about helping us do these calculations. But the thing I want to kind of draw your attention to is, if we did regular reactions here, these bond dissociation energies are quite high. 2 to 4, maybe even 600 kilojoules per mole right here. However, if we look at something down here in this low corner here, we actually have a whole set of things where that bond dissociation energy are at 200 and below. So we have these bond dissociations at 200 and below. So that means that they more easily form radicals, okay? And not only do they more easily form radicals, they are the lowest in energy of forming this dissociation bond. So we would tend to use these to act as initiators to generate radicals and reactions. In fact, this entire set right here is what we're going to learn are called free radical initiators. And it has everything to do with the idea that these are so easy to dissociate compared with all the other bonds. Notice all those other bonds. I mean, we're looking at, 3, 4, 5, 600. These are all below 200. In fact, one of the really good ones right here is below 100 even. So we're going to start to look, and that's why we have certain things classified as initiators. Okay, so let's get some trends. Okay, just like there's trends on the periodic table and trends on carbocations, let's look at our radical trends. Trends use the acid-base substitution elimination. Our trends used previously include those. Okay, so let's look at that first with decreasing electronegativity decreases bond strength. Okay, think about that. The more polar the bond is, the more the stronger that bond is. Okay, so decreasing electronegativity decreases bond strength, which means the higher electronegativity difference between atoms, the stronger the bond is. So if we look at carbon and fluorine right here, Fluorine has an electronegativity of 4, carbon has an electronegativity of 2.5, and that's the biggest difference we get in this series. And we see it has the largest bond dissociation energy. Moving on to an oxygen, which is that one step over from fluorine, it goes down not quite 75 kilojoules per mole, but then going from oxygen to nitrogen, it goes down again. Okay. So think about it as the decreasing electronegativity decreases bond strength. Okay. So, and that works between carbons and other groups, but it also works with hydrogen as well. Okay. So if you have a hydrogen bonded to an electronegative atom, the decreasing bonds, the decreasing electronegativity decreases that bond strength. So we have oxygen is more electronegative than nitrogen, and therefore it has a stronger bond. And nitrogen is more electronegative than carbon, and therefore it has a stronger bond. Now, the other way to think about this is the difference in electronegativity between these two atoms, because one is more slightly positive and one is more negative. You can think that it makes a shorter, stronger bond. So that difference in electronegativity is making a shorter, stronger bond because it has more ion-like character. Okay, so the next thing is decreasing electronegativity and increasing the size decreases the bond strength. So now let's think about going from fluorine down on the halogens, right? If we go from fluorine down on the halogens, fluorine is the smallest of the halogens and has a very short, very strong carbon-fluorine bond. We go down one to chlorine, okay? Chlorine is bigger because it has a 3 energy level, and so it has a longer bond. That longer bond creates a weaker bond because the nuclei are further apart. Now we go down one more, bromine. Bromine is much larger. There's a much bigger distance between the nuclei and the carbon, therefore leading to a weaker bond. And then, of course, iodine is big and fluffy. It's such a weak bond. It's a great leaving group. Okay, so we follow that trend the same. In addition, the decreasing S character decreases bond strength. Okay, so that means that our SP, which is 50% P, 50% S, is a weaker bond than having a sp2 hybridized, where it's 33% S, and that comes up a little bit to 494. And then our sp3, which is only 1/4% S, is our strongest. Decreasing S character decreases bond strength. It seems backwards, but oh, these numbers are backwards, that's why. So this is the strongest one because it has the most S character, then this one and this one. So this is the weaker of the, more acidic. Yeah, so this is worded incorrectly, I'm sorry. What it should say is that the more S character decreases bond strength. This is 50% S character, and it is the weakest bond, and it's also the most acidic. This is 25% S character, and it is the strongest bond, and it is the least acidic. So I think the words are backwards on that one, sorry. Okay. The next thing is increasing hyperconjugation decreases bond strength. Remember what hyperconjugation is. Hyperconjugation is that overlap with the adjacent sp3 hybridized bonds. Okay, so we have here that our methyl hydrogen here is stronger than our ethyl hydrogen bond, which is stronger than our isopropyl hydrogen bond, which is stronger than our T-butyl bond. Notice it's not a big difference. Yeah, the more S character, the more acidic. Yeah, that is true. So that means that our decreasing bond strength is our methyl is stronger than our primary, secondary, and tertiary. And that's independent of electronegativity, size, and hybridization. Okay. Because those adjacent things are able to back donate electron density, we can change that bond strength. Okay. So the other thing that we need to remember is that our bond dissociation energy indicates the ease of radical formation. Remember on that previous table, all of those ones below 200 we call initiators because they form radicals more easily than most of those other bonds. Okay, so let's look at trends in the bond dissociation energy or the formation of a radical, okay? So in the case of that, because of the methyl group here being the strongest bond, it needs the most energy to break that bond, okay? So think about that. So that primary radical needs more energy to create, okay? Our methyl radical, sorry. Now, as we go down, this is less stable, and it has a lower bond dissociation energy, meaning it's easier to generate than that methyl radical. So methyl radical is the hardest one to generate than a primary radical. And again, now that our bond is weakening still, right here, we get to another jump down, making that secondary radical easier to obtain. There must be a typo here because this should be higher. Sorry, I'll look that up. And so that secondary radical is easier to obtain than the primary radical. And of course, the best of us all is our tertiary radical. So our tertiary radical is more stable than the primary radical because of hyperconjugation. And here's a little diagram to remind you what hyperconjugation is. The sp3 orbital of the adjacent material interacts through space to stabilize the radical. Notice only one of the sp3 is going to be able to overlap with that radical, okay? The other two are going to be out of playing with that p orbital on the adjacent carbon, so only one of them can hyperconjugate. So if you get, in this case, a primary where you have one hyperconjugating, now you add another carbon over here so you can get a second hyperconjugation, and then another carbon over here to a third hyperconjugation. Just like stabilizing a carbocation, that hyperconjugation is how we can stabilize those tertiary radicals. So methyl is the hardest to make and least stable. Tertiary is the easiest to make and most stable. Okay. So then the next thing we need to think about is resonance. Okay. Remember, resonance really stabilized carbocations. If we had a carbocation next to a double bond, it could share that partial positive charge across those. That same thing exists in our hyperconjugation of radicals. So if we look at bond strength, the tertiary bond strength is greater than allylic, which is the one over from the double bond, and it's greater than benzylic, which is this one here, the alpha carbon off a benzene ring. So that means that if this tertiary radical is stable, that means that the allylic one is going to be more stable because it has a weaker norm. If we look at stability, the tertiary is going to be less stable than the allylic radical, and that means the benzylic radical is going to be the most stable. And just like before, it's all about resonance, okay? The fact that if we had this radical here, allylic, which is that one carbon off the double bond, we can then move them back and forth, back and forth, back and forth through resonance here to generate our hybrid structure here, where our unpaired electron is covering over two atoms, meaning instead of having a destabilization or a cation associated with having not an octet on your carbon, you can share that charge. Now, notice that how many different resonance structures we have with benzene. With this benzylic system, where we create the radical, that one carbon off, we can get 5 different resonance contributors, giving us our hybridized look structure as having those charges spread over 4 atoms. And that's why resonance increases stabilities of radicals as well. Okay, so certain functional groups can also stabilize them. And what we look at when we look at functional groups is the availability of a pi bond or a lone pair. Okay, so in the case of this with a nitrile group, this is an electron withdrawing groups right here. This is an electron donating group. These are electron, okay, let me circle. Donating groups are in green here and withdrawing groups are in red now. Okay, so we have this right here, double bond. That double bond can contribute to a new resonance structure, so we can have the radical either on the carbon or on this nitrogen, therefore spreading that charge out over 2 different resonance structures. When we have a carbonyl, remember we have lone pairs up here on our carbonyl, so it does the exact same thing, but it doesn't move 2 electrons like it did before. We're moving 1 electron in. From there, 1 electron in from the carbonyl to create a new sigma bond, a new pi bond, and that leaves the remaining lone electron on the adjacent atom. So notice that this resonance structure is giving us. So that's with our electron withdrawing groups, but can it work with electron donating groups? Yeah, in the case of donating groups, we're probably looking at the lone pair on an adjacent atom. Notice in these, whenever we have a double bond, it's going to be the 1 and 3 positions that are going to hold those radicals. When we have lone pairs adjacent to our radical created, we're going to use the electrons from that lone pair. So think about electron donating groups are going to be adjacent and give us structures like this. 1 electron from the oxygen lone pair goes to the radical to give us a double charge species. Notice we have a negative charge here and a positive charge here. Notice it didn't create a sigma bond here. It's actually transferring an electron and creating a di-charged system. Okay, so, but it's all because of the lone pair. Here again, we have one of the electrons from the lone pair going here, giving us a positive charge on one atom, a negative charge on the other, and therefore it's a contributing structure. Okay, so notice the difference. When we have the double bonds, it's going to be the 1 and 3. That's where the radical is going to associate with the position 1 and position 3. It's going to skip over an atom. But in the case where we have the lone pair directly next to the radical, it's going to be that 1, 2, that really adjacent system. Okay, so let's talk about stable radicals. Okay, so I said they're really reactive. However, if you can delocalize that radical, or if you have something that actually has a significant stability, either due to resonance structure, electron stability, or hindrance, you can actually put these in the bottle and they will stay radicals for a long period of time. So let's look at the first one here. This is a benzene ring with 3 two-butyl groups on it. And so then we actually had a phenol, we had a OH here. And so that means we broke off a hydrogen radical here to generate this T-butoxy radical. Okay, now the reason it's stable is, number one, it can resonance stabilize itself here, but then it also has these 2 big bulky groups. So it's got an electronic component for resonance, but then it has a steric component. So even when it's there, and or the radicals here or here or here, it's protected by sterics. Okay. In the case of this one, this is tetramethyl pyridine and oxide, and it also has these methyl groups helping stabilize it, but it's also shared between this nitrogen and this oxygen back and forth, and those methyl groups help protect that radical from being reactive. Another way to do it is to have these nice electronic drawing groups on our system here. So this is another radical where we have the radical is, you know, more than likely stabilized on this nitrogen, but it can delocalize around the ring. But then it has these large protecting groups keeping it from reacting. And in this case here, we have our radical here, but it also can move around into the ring and generate it all the way over here. That radical is conjugated all the way through that system and can be used that way. Notice in this, electron withdrawing groups and electron donating groups, it doesn't matter. It's not like with a nucleophile or electrophile that would change your acid strength due to an electron withdrawing group or not. It's all about the resonance stability and the ability. So for example, we have, almost no donation. These are withdrawing. This is probably donating. So we have different ways. So radicals adjacent to those big bulky groups keep it from reacting. Something has to come in just right to be able to get to that. And that's why these are really nice, cool, stable radical in a bottle. You can imagine just sitting on the shelf, it'll stay stable there for years. Although most of the time, when other forms of radicals are, they just zip up and go away. Okay, so I said before, on that big table there, we had that group at the bottom that had very small bond dissociation energies, and that gave weak. And that means they were weak, they were easy to break, okay? So that means that even with low energy, like light or heat, we can break that apart, dissociate that to give us two equivalents of radical. And then those two equivalent radicals can go off and initiate or react with other substrates. Okay. So in the case of this peroxide, which is an alcohol right here with an extra oxygen on it to give us what we call a peroxide, when it breaks apart, it gives us two oxygen radicals that can go on and react. Another very common one that is really stable once it forms is the Per-Benzoil Peroxide, this dibenzoyl peroxide. Now, the reason it's stable is that we have, not only do we have the formation, we have a weak bond that breaks apart very easily. It's the one down here below 100, but that radical is stabilized around here and then can generate this phenyl radical and extrude CO2. So that phenyl radical is also nice and stable because it has conjugation around the ring. Okay. So the key here was the low bond dissociation energy to create them. And now they're stable enough to go off and do other chemistry. So I said that radical reactions are not like the ones we have, where we just have the electrons come in and form our new sigma bond. Okay. So, and that when a radical comes in contact with a neutral species, it actually generates a new radical because it only used one of those electrons to create its new sigma bond. Therefore, there's actually three different steps to every radical reaction. Okay. The first step is what we call initiation, and that's the creation of the first radical. So in the case of something where you don't want to use an initiator, you can use high heat or light to generate something like a chlorine radical. In this case here, what we're doing is we're taking chlorine radical and we're hitting it with light to generate our two equivalents of our chlorine radical. Okay. Now, we don't generate very much of it, so there's only a small amount of that radical generated at any one time. And that's okay, because remember, every time this radical reacts with something, it generates another radical. Okay, so that's our first step in the reaction, is that we can get this formation here. Notice in this main chain here, we really can't stop it. The more chlorine you add, the more you get to the end here. And they'll each substitute the hydrogen for chlorine as you go on and on and on, and generate that same number of equivalents of HCl. So we generate one equivalent HCl here, two here, three here, and four at the end. Okay, so we've initiated the reaction. We've created our radicals to start. What do the radicals do? Well, they're going to go and react with something to create a sigma bond and a new radical. Okay, so we call that the propagation step, because we are consuming a radical, but we're always generating a radical too. So that means the reaction just spontaneously self-perpetuates until you end up quenching two radicals at the end. So let's look at that reaction. So there's a lot of different ways this can happen. Like let's say, okay, we start with this chlorine radical. Notice it has a single barb on these things, meaning one electron's moving. We're going to single barb it over here to create a new sigma bond between this hydrogen and this chlorine. But notice what it does. It used one of those electrons from the hydrogen sigma bond to carbon, leaving the other electron on the carbon. What does that mean? We didn't consume our radical creating that new bond. We maintained the same number of radicals we had. Okay, so that's why this reaction self-propagates. Okay, so remember we had very little of this in there, and we had mostly the chlorine. Well, now our chlorine can act as a reactant with our new radical. Our single electron, single barb here, reaches out and generates a new chlorine carbon bond with one electron from the chlorine, one electron from the carbon. But notice we generate another radical. Okay, so the first one, we call that hydrogen abstraction because we removed a hydrogen from the system, and that generated a carbon radical. The second one here, we actually call this halogen abstraction because we're taking one of the halogen, but we generated a chlorine radical. So we still have the same number of radicals we started with. Okay, so let's go to the next step. What else can happen? Well, the other thing that can happen is, well, we had a little bit of chlorine, and we can notice the substrate is now the chlorinated version here. We can do that hydrogen abstraction again, create another equivalent HCl, but we create a new radical. So that radical can go react with another equivalent chlorine, to give us our new chlorine dichloro compound. And it goes again and again and again and again and again until you run out of things to react with. You're running out of chlorine gas, or the chlorine, or you're running out of the methane gas. And all you left at the end of the reaction is everything's been consumed, except now you only have a few radicals just laying around. Everything else has gone to, all the hydrogens have been converted to HCl, and all the chlorine have been added to carbon. So now we have to stop the reaction. And this is the termination step. This only happens when everything else is consumed. We actually have that low concentration of radicals around, and they start to combine each other. Okay. Now this can happen in the reaction itself, but we'll generate chlorine and we can use that. So that's great. The other way to do it is to have the chlorine radical react with the carbon radical, and that's great because that generates a final product. The other thing that can happen is we can actually get a carbon radical, terminate with a carbon radical, and we'll generate a slightly larger carbon-carbon chain. Okay. Now, the other thing that can happen, which is not really desirable, is that the radicals can terminate on the walls of the vessel. Now, if you do that, then your reaction probably doesn't go to completion. You want everything to be consumed until you're at the end of the reaction, and then you want those final radicals to recombine, radical combining to form a neutral sigma bond. Okay, so the other thing that can happen here is if you generate too many radicals at once, they're going the reaction is going to speed up to what we call auto-initiated, auto-catalyzed reactions, where they speed up so much, they heat up so much, they generate even more radicals and more radicals, and so they actually can have reactors blow up if you generate too many radicals at one time, because you'll have so many reactions happening at once, and most of the reaction will be containing radical systems. Okay, so the key here is there's 3 steps to your radical reactions. You have to initiate a radical, typically with heat or light, or an initiator, like one of those weak bond dissociation bonds, like a peroxide or a carboxylic acid. The second step is propagation. It's going to keep reacting and forming the same number of radicals you generated initially until you end up with only a few radicals left in the reaction. Those radicals start to combine with each other and terminate the reaction. Step 3. Okay, so there's 3 steps in this reaction always. Okay, so now that we know that, we can actually get some selectivity in this based on the bond dissociation energy and the bond energy formed. Okay, So let's look at that and see if we can be selective with this. Okay, we have a fluorine-fluorine bond, and we're going to hit it with UV light, okay? And we're just going to react it with propane. Okay. All right, this will be my last slide, and we'll stop for the day. And if we do this UV light, we get about 30% of it being the secondary fluorination, and we get 70% of it being the primary fluorination, okay? Now, it will produce, if you add more fluorine, it'll produce multiple fluorinated products. And that is something we sometimes want, but sometimes don't. Sometimes you want just one equivalent of there. Now let's look at the bond dissociation energies of the different halogens. Okay, so for fluorine, we have a pretty low bond dissociation energy. Chlorine is higher. Then bromine drops down again, and iodine is just below that of fluorine. So we have three different bond dissociations for these different halogens. So we should see a different behavior in each of these halogens based on that bond dissociation energy, because the initiation step is the breaking of that halogen bond. Okay. Now, of course, the propagation step is that reaction with the halogen with the substrate to generate a new radical. And then, of course, we can get fluorination from that point and create, that's the hydrogen abstraction is one of those reactions. And then the breaking of the halogen abstraction, where here we're abstracting a hydrogen from the substrate. Here we're abstracting a halogen by the substrate radical. And then, of course, our termination steps are where we end up quenching them all at the end. Okay. So let's look at the effect of having different things with that selectivity. Okay, so fluorine was about 160. Chlorine was the highest energy. Okay, that was the highest energy to break. And we have, roughly a 50-50 mixture. Bromine was a little bit lower, similar to that of fluorine. And we got to a 92% of the more substituted product and only 8% of the primary product. And iodine gets almost nothing, okay? And it has a lower bond association than fluorine. So what's happening here? Okay. So first of all, what should you get, okay? So statistically, right here, there are 2 hydrogens here, and there are 3 hydrogens here, okay? So by statistics, we should get, you have 1 in 2 chance of getting a hydrogen abstraction here. You have a 1 in 3 chance of getting a hydrogen abstraction here, which means you only have a 25% chance of getting a reaction at that secondary carbon, and you have a 75% chance of getting it at that primary carbon. So why is it different? Why does it change? Okay. I think it has something to do with the propagation step here. If you look at your different ways of propagating, if you do your hydrogen abstraction in your secondary hydrogen here, you're going to get your secondary radical, and then that's going to react with your halogen. Okay. So the overall reaction is going to give us that there. So this is our propagation to get to our primary alkyl halide. This is our propagation to get to our secondary alkyl halide. Okay. So what's different? If the mechanism's the same for all of these, why are they different? Okay. And we'll have to come back on Wednesday to figure out why, because it's just past 10:50. All right. I'm going to go ahead and stop recording and let you ask questions.